Well, today's really lucky day. You get to play a double header. Two completely different experiments all the same day. We'll start with the qualitative analysis for the group 1 ions. Group 1 here refers to the classic quantitative analysis scheme, not the periodic table. You'll get a solution containing one or more of the following ions: the mercurous ion, the silver ion, the lead ion. And you'll determine which of these are present. These ions are grouped together because of all common ions, only these three form soluble chlorides. In this analysis, first you'll separate the group 1 cations from any other cation which may be present. And once you isolate these cations, then you'll separate each from the other. And after separation, a test will be run to confirm the presence or absence of the cation. Now, initially, you'll carry out this separation and identification using a solution known to contain all three cations. This is the known. In this way, you will learn how each cation reacts. Then, you will carry out the analysis on your unknown. The chemistry of what you're doing is summarized in this flow diagram. You'll start out with a solution which contains one or more of the following ions, and you will separate these from anything else there by adding chloride ion, HCl. This will precipitate out these as the chlorides. Now, to separate ions, you will then add hot water, which will dissolve the chloride so that you'll have separated the lead and remain behind as precipitates then silver chloride and mercurous chloride. These separate by dissolving out the silver chloride as the complex by adding ammonia. Now you have separated the three ions at this point, and you are running the confirmatory test. The black color of the mercury here is confirmatory test for mercury. This color solution, when acidified, should yield a white precipitate of silver chloride if silver is present. And this solution here, when chromate ion is added, should a yellow precipitate if lead is present. Well, let's actually go through and do an unknown here. In the first step, we'll add HCl to our unknown to precipitate out the chlorides of any of the group 1 ions that are present. To do that, then, what we'll do is take about a milliliter of the unknown, or 20 drops. Add to that the HCl. And as you see, as we add the HCl, you're forming a white precipitate there. We're going to next separate this precipitate by using the centrifuge. Here's the centrifuge which we'll be using. The purpose of the centrifuge is to set up the separation using centrifugal force. Here the two phases being separated are the solid and the solution. Here's a close-up of the mixture we're separating. To use a centrifuge, put your tube with the sample in one of the holes of the centrifuge, and then you'll put in a counterbalancing tube opposite it. Fill it approximately the same amount and put it so that it is opposite. Then turn on the centrifuge. In about 30 seconds, you can turn off the centrifuge. Separation should be completed. Stop it, put your fingers so that they are in the same direction as the spin, and then lightly touch the side here. There's your separation. As you can see, it is completely separated. In using the centrifuge, remember, make sure it's balanced before you turn it on, and then watch it when it's spinning, so it doesn't tend to move around. And don't let the spinning head touch anything, particularly the electrical cord. You can cut it. And finally, watch your fingers. All right, let's go over that one more time then. Make sure that when you put something in to get centrifuge, you put a counterbalancing tube in. Then when you turn it on, make sure you keep watching it so that the centrifuge doesn't tend to wog. Make sure it doesn't touch anything such as the cord. Keep your hands away from the centrifuge while spinning, particularly on the top here. And then when you turn it off and you want to slow down, make sure your fingers are in the direction of the spin, and then just lightly, gently slow it down. Well, at this point, we've precipitated out and washed the chlorides of whatever group 1 ions are present. Now what we're going to do is we're going to add some water. And then we're going to heat this, and that way we're going to separate the soluble lead chloride from the insoluble silver chloride and mercurous chloride. All right, we'll use a boiling water bath to heat the sample here. Don't forget to use a stir to make sure that everything is mixed so that all the lead chloride, if any is in there, will dissolve. And also, don't forget, when you're centrifuging and decanting the supernatant liquid, make sure the solution is still hot so the lead chloride remains in solution. Well, now we've separated out any lead which might have been present using hot water. And what we're going to do at this point is use ammonia to separate the silver, which might be in here, from any mercury which might be in here. And we'll use these equations which you see over here. Here's a close-up of what happens to our unknown when ammonia is added. Now we'll centrifuge this and test the supernatant liquid for silver. At this point, we've completed the separation of ions. This tube contains any mercury, this tube contains any silver, and this tube contains any lead. And we're now starting the confirmation tests. The confirmation test for mercury involves adding ammonia to the mercurous chloride to get a black precipitate of mercury metal itself. As you can see, what we just did produced that black precipitate, so this is a confirmation of the presence of the mercurous ion in the original unknown. The confirmation test for silver involves the acidification of the ammoniacal solution which we've just prepared. If silver is present, then we'll get a precipitate of silver chloride. Let's see if that happens. Again, we'll do that in close-up, and we'll add the nitric acid to the tube here. And you can see that there is this cloudiness, which means that a precipitate is forming. The confirmation test for lead involves adding chromate ion to a slightly acidic solution. The precipitation of the yellow solid lead chromate confirms the presence of lead. Let's see what happens in our unknown. Again, in close-up, we'll add a drop of acetic acid, then we'll add some potassium chromate, and as you can see, no precipitate is forming here. We'll stir that up a little bit. There's no precipitate formed. So there are the results of our analysis. For mercury, we get a confirmatory black precipitate. For silver, we get a confirmatory milky white precipitate. And for lead, we get only a clear yellow-orange solution. Therefore, there is an absence of lead. Now we'll turn our attention to pH. pH is a term important in describing aqueous solutions of acids or bases. This is one of our pH meters. At this point, I'd like to point out that although we're showing this after doing group 1, you may wish to do it first or in the middle of group 1 to avoid the crowds. Well, to start, let me ask, what is pH? pH is defined as the minus log of the hydrogen ion concentration. Now, pure water has a hydrogen ion concentration of 1 times 10 to the minus 7th molar. That's at 25 degrees. That gives it a pH of 7. Now, this is a very small number, and therefore small traces of acid or base can markedly affect the pH of pure water. Because of this, it is actually very unusual to get a pH reading of 7 for plain distilled water. Now, if you add acid to water, you will increase the hydrogen ion concentration and therefore lower the pH. On the other hand, if you add base to water, you will decrease the hydrogen ion concentration and increase the pH. To get a little better understanding of pH and acidity, we can use this equation. Now, when you put acids in water, they dissociate to hydrogen ion and the corresponding anion. Now, if you get almost all or completely all of the acid dissociating, such an acid is called strong. On the other hand, if you get very little dissociation and most of the acid remains undissociated, such an acid is called weak. Now, if we take either a weak or a strong acid, and we take one equivalent of these, we'll find that if we titrate it with base, it'll take exactly the same amount of base, because the base will neutralize the acids regardless of whether it's dissociated or undissociated. But on the other hand, if we take the same one equivalent of acid and put it in 1 liter of water, the strong acid, being completely dissociated or almost completely dissociated, will have a higher hydrogen ion concentration and therefore a lower pH. Now, the relationship for weak acids and concentration and pH is rather complex, and you'll learn about that next semester. But for strong acids, the relationship is rather straightforward. Now, for monoprotic acids such as hydrogen chloride, you have a certain concentration of hydrogen chloride. Say the concentration is 0.01 molar. Since the hydrogen chloride is completely dissociated, that means that the hydrogen ion concentration is also 0.01 molar. And therefore, the pH of that solution is 2. Well, let's make an actual measurement now. Here again then is the pH meter. The pH meter has 3 control knobs. The top one is called calibrate. It's used to calibrate your pH meter to pH 7. Like almost all instruments, the pH meter must be calibrated before use. The second knob here is called temperature, and it allows a second point of calibration for your pH meter. Do not touch this knob because it has been set for you by the instructor. The third knob down here is essentially an on-off switch. If you want to read a pH, you turn it to pH. If you want to then do something with the electrodes, you turn it to standby. The pH, of course, is read on the meter here, and the pH is sensed with the electrodes here. Now let's take a closer look at the electrodes. Here's a close-up of the bottom of the electrodes. The larger bulb on this side is the glass electrode, which is sensitive to changes in pH, and the small tube on this side is the end of the reference electrode. Well, let's make our measurements now. To do that, first we'll calibrate the pH meter. We have the pH meter sitting in the pH 7 buffer here. And to calibrate this then, what we'll do is turn the meter to the pH reading, and with the calibration knob, we will adjust the needle until it is exactly on 7.00. Now the meter is calibrated, and we will make our measurement. To do that, we put this on standby, wash off our electrode, When you handle the electrode, be very careful that you don't tip it. As you can see, there's a hole here which allows filling of the reference electrode with saturated potassium chloride solution. So you must not tip it because the solution will run out. But anyhow, you wash off the electrode, pat them dry with a clean paper towel, and then you're ready to make your measurement of the solution that you brought here. Bring your solution into the electrode. The electrodes must be covered, at least those tips that you saw there. Swirl it around, bring it to pH, and then you can do your reading. This is water, which is reading a little bit different than exactly 7. We'll take a close-up on that in just a second here. Here's a close-up of that reading. As you can see, the water sample drifted down a little bit, and now it's reading 6.39, a pH of 6.39. Well, what we'll do now is put 10 drops of sodium hydroxide in here. All right, that's the 10 drops. And now I'll swirl the beaker, and as you can see as I swirl it, the pH is rising here. Now, before we can take this reading, we must correct for the parallax error. As you can see, the camera's in the wrong place, and you not only can see the mirror, the needle itself, but you can see its reflection in the mirror. When this happens, you will have a parallax error in reading, so we'll have to move the camera to eliminate that parallax error. Here's that reading without the parallax error, and as you can see, it is reading 11.33. So with 10 drops of sodium hydroxide in that water, the pH rose to 11.33. Now, if we want to add something to this solution, we can do that. I'll just add some more drops of sodium hydroxide to this. And without changing it from the pH reading or anything else, just swirl it and take another reading. However, when we are through making measurements with this solution and want to change the solution, what we must do is put this to standby, take the electrode, clean off the electrode, blot the electrode clean, and then put our other solution, or if we're through, we'll just put it in the pH 7 buffer. Well, to summarize then, whenever you get to the pH meter, the first thing you do is make sure the pH meter is on standby, and you take the electrodes and you rinse them off and pat them dry. Then you calibrate the pH meter with the pH 7 buffer. This you do, of course, with the pH meter in the pH position. Once it's calibrated, you again rinse off the electrodes and blot them dry. This again in the standby position, and then you put your solution to be measured and put the electrodes in that solution. The measurement is done in the pH position. Now, you can continue to use that same solution with the electrodes in the solution and on the pH if you want to add something to that solution. But once you're through with that solution, you want to take the electrodes out, you then must put it into standby and take out the electrodes. The electrodes must then be rinsed off, and then they can be used for whatever else you're doing. Or if you're through, then just let someone else use the pH meter. Well, I think at this point you're all set to start.